All right, well, thank you very much. It's really an honor to be here, and it's very exciting to be able to talk about these results. So let's hope it's a good send-off for the last talk in the series. So the result I'm talking about is demonstrating fusion ignition in the laboratory for the very first time. It's a result that has been several decades in the making, and as such, I am really representing a very large team here, not only from Lawrence Livermore National Lab, but really from labs all across the country and even across the world, as well as various industry partners that we're working with. And so on December 5th, 2022, at around 1 a.m. in the morning, we performed an experiment at the National Ignition Facility, or the NIF, as we call it. It's the biggest laser, the most energetic laser in the world. And in that experiment, the NIF delivered 2 megajoules of laser energy, just over 2 megajoules, to a fusion target. It compressed it to extreme temperatures and densities, and that started fusion reactions, which released just over 3 megajoules of energy. So we got more energy out than we put in. That meets the definition of fusion ignition by the National Academy of Sciences, and it's the first time anyone was ever able to do that in the lab. This accomplishment is the result of 6 decades of research, and it required focused effort in high energy density sciences, as well as target diagnostics and laser capabilities. It now provides unprecedented capabilities for stockpile stewardship. This is one of the key missions of the lab, of Lawrence Livermore National Lab, but it also provides the scientific foundation for inertial fusion energy, which is using this technology to actually put energy on the grid, and that, until recently, really has been the stuff of science fiction. Let's see. There we go. So in this talk, I will give you a brief overview of what is fusion ignition, and how do we do it on the NIF. I will tell you how we got there, specifically the last sort of 10 years of experiments that we've done on the NIF, and why did it take us so long to get to this point. And then I'll tell you a little bit about where we're going to go from here and what this means for inertial fusion energy. So just starting with the basics here, you have all seen a working fusion reactor. You only need to look up when the sky is clear, because fusion is the process that powers the sun and the stars. It's the process by which you take 2 light nuclei, you smash them together so hard that they actually stick together, and that produces energy. And that's because the end product is actually lighter than the initial ingredients. And so by Einstein's equation, E equals mc squared, that difference in mass is released as energy. You may be familiar with the opposite process, which is nuclear fission. That's being used across the world in power plants to generate electricity. And so you may be wondering, well, if I break the atom and if I fuse it, I get energy both times. It turns out there's a transition point at iron at 26. Below that, lighter nuclei, when you fuse them, you release energy. And above that, heavier nuclei, if you break them apart, you release energy. In either case, you lose mass in the process, and that's the energy you free. So the 2 easiest elements to fuse together are tritium and deuterium, as depicted here in this cartoon. These are hydrogen isotopes, so it's proton with 1 or 2 extra neutrons, and that's the reaction we use in our experiments on the NIF. And if you smash these 2 together, you get a helium core, that's an alpha particle, as well as a free neutron, and then you get lots of energy out of it. It's about 17.5 MeV per reaction, and that's a lot of energy. Just for reference, in terms of energy per mass, this is 4 million times higher than burning oil or coal. So it's a very, very energetic process. And basically that is what we're trying to do in the lab. We're trying to light up a little star and get more energy out than we put in. The problem is, of course, these 2 elements don't actually want to be anywhere near each other. They're positively charged, and so they need to be very, very hot, very energetic in order to get close enough such that you overcome the Coulomb repulsion and the nuclear force starts to dominate. So that means you're working in a plasma environment. And also you actually want to keep them close enough to each other such that the probability for a reaction is high. And that's typically referred to as the confinement problem. So there are different ways of generating a sustainable fusion reaction. The one that nature came up with is shown on the left-hand side here, and that's to just make it really, really big. So the sun weighs 2 times 10 to the 30 kilograms. That's 300,000 times the weight of the Earth. And through its own gravitational pull, it generates the pressures and temperatures needed for a sustained fusion reaction. However, this is somewhat impractical to do in the lab. And so we came up with 2 alternative approaches, and by we I mean humanity rather than Lawrence Livermore National Lab. There is magnetic confinement, of which I will say very little because I don't know anything about it. But here you have a relatively low density plasma, and it's confined for several seconds, sort of 10 seconds-ish, by a magnetic field, and that way you can potentially release more energy than you put in, and that's being used in the ITER reactor that's currently being built in France. And then you have inertial confinement fusion, which is shown here on the right-hand side, and that's what we use at Lawrence Livermore National Lab. And here you have a confinement time of only about 100 picoseconds or so, 10-ish orders of magnitude lower, but our densities are also much, much higher. And it's really that product of confinement times pressure and temperature that tells you about your proximity to ignition, and you can express that in different ways for magnetic fusion and ICF, but I'll come back to that a couple of times. Okay, so, are we doing this? No. There we go. So the way we actually do this on a NIF is shown here. So the NIF actually has 192 laser beams, and we use half of them focused onto our target from the top and half from the bottom. And the target is this cylinder. It's about 1 centimeter in size, so 10 millimeters by 6 millimeters. And this is what we call a Hohlraum. It's a German word, basically means empty room. And so this is a hollow cylinder. The laser beams are focused to the inside wall of this cylinder. And at the center of this cylinder, that's actually the thing we care about. It's a little capsule about the size of a peppercorn, 2 millimeters in diameter. And inside that capsule, that's where the DT fuel is. That's the elements we want to fuse together. And so what happens here is the laser deposits its energy into the cylinder. So over 10 nanoseconds, you dump 2 megajoules into this small can. It heats it up to about 3.5 million degrees. And so this can turns into an X-ray oven, essentially. And so that now heats the outer layer of this capsule. It pretty much instantly turns into a plasma and explodes outwards. And because you have Newton's third law and the rocket equation, that means everything on the inside of this exploding layer needs to go towards the center. That's the only direction it can go. And so now your capsule is imploding towards the center at a velocity of about 400 kilometers per second. That's about 1 million miles per hour. And eventually, it will stagnate on itself when it can't be compressed any further. At that point, it becomes very hot, very dense. So you've converted that kinetic energy of the implosion into temperature and pressure. It doesn't actually want to stay that way. So it will immediately then explode outwards again as soon as you take as you turn the laser off. Yes, please. No, it's so the inside of the cylinder is at a very, very low pressure, but it's not. That's not to drive the implosion. It's to control how the beam interacts with the Hohlraum itself. But because so imagine the outside layer of this capsule immediately vaporizes and turns into a plasma. That means it's expanding outwards, and that means because of momentum conservation, that means stuff on the inside has to go the other way, because otherwise your momentum isn't conserved. And that's the same idea of a rocket. You push a lot of stuff out at one end, so the other end goes that way. Say again? I'm not sure what thermal implosion means. That sort of stuff is flying in this direction, and so the other stuff has to go this way. And so because it's flying off spherically symmetric, that means the only place it can go is towards the center. And so everything on the inside of that exploding layer is being compressed.
So what is this thing made of?
I'll get to that. Oh. But the cylinder is high Z, so typically we use gold-lined uranium because that's very efficient at converting laser into X-rays. The higher Z, the better. And the capsule itself is made out of high-density carbon. It's basically artificial diamond, which has many, many reasons that we can go into if you want. And then, of course, the inside is DT, is the fuel, the deuterium-tritium fuel. Okay, so this thing implodes. Eventually it stagnates on itself, and now you've converted your kinetic energy into pressure and temperature. And this is driving me nuts. And now you've created a very, very hot spot at the center of this implosion. And if you get it right, if you get the implosion sufficiently round and sufficiently fast, you dump enough energy into the implosion, then you get a small spot at the center that reaches temperatures of about 100 million degrees. That's 10 times hotter than the center of the sun. And then the fuel, the DT fuel around that spot reaches densities of about 100 times that of lead. So it's very, very dense. And so the conditions in the hotspot are now hot enough that you start getting fusion reactions. And that's not your sun yet, that's just a spark. But these fusion reactions, yes please.
I'm so sorry. I have a really naive question, but how can any material sustain such temperature? Like human-made material? I'm pretty sure you're going to use it.
Oh, well, that thing is gone after the experiment. There's nothing left of the target. So everything will turn into a plasma.
But you must have like some, it's not just like this, but you have some sort of casing.
Yeah, so this thing is located at the center of a 10-meter vacuum chamber. So we're talking very high numbers here in terms of temperatures and energies, right? 2 megajoules of laser energy. In reality, that's not actually a lot. It's that's not going to blow up a house or something, right? This is about the energy content that you have in a battery in an electric bike. It's not actually a lot of energy. It's just very concentrated, right? That's why it's so hot. So your chamber isn't going to blow up from this. No, because yeah. Okay. Any more questions? Okay. All right. So we made this very dense. We made it very hot. The alpha particles that are now generated in these initial fusion reactions, they actually don't make it out of the target because they're now deposited in the fuel that surrounds the hotspot because that fuel is such a high density, right? 100 times of lead. And so what they do is they sort of keep the temperature up. They keep the pressure on. And now, if you get it right, then you can have a burn wave that propagates through the fuel, through the DT, and you release more energy through these reactions than what you put in initially to drive the implosion. And so that's the idea. Getting the spark is not very difficult, but it's getting the conditions right such that you have a propagating burn wave and you get more energy out than you put in. Okay. So in principle, this is how you do it, and we've actually known how to do this in principle for a long time. Ignition was initially developed, the idea was developed by John Knuckles in the late 1950s. Interestingly, at the time, there wasn't actually the technology to drive this implosion, to reach these high densities of the DT that you need for a sustained reaction. This was 10 years before we went to the moon, so a long time ago. In terms of science. But luckily in the 1960s, or in 1960, the laser was invented, and Knuckles very quickly realized the potential of this new technology to drive inertial confinement fusion experiments. The research was initially classified. It was declassified in 1972 when they published a paper in Nature. But pretty much immediately, the lab started developing ever more powerful laser facilities to act as a driver for such experiments. In the mid-1960s, we started with a Janus laser, which by today's standard had a measly 200 joules. And eventually this culminated in the National Ignition Facility with, at the beginning, 1.9 megajoules of peak energy. We've actually upped this slightly since then. The National Ignition Facility is now the biggest laser in the world, or actually it has been ever since it was commissioned. It started construction in 97, but since 2010 it's been fully operational, and in 2011 we did actually, no, in late 2010, we did the first ET experiments, basically attempts to light up a little star. Still, it took us about 10 years of experiments on the facility to get anywhere near relevant ignition-relevant conditions. And some of the key highlights here are shown on this plot. And in 2020, we did the first experiment where we got what we call a burning plasma. So we had a yield of over 100 kilojoules, again, with about 2 megajoules of laser in, so that's not a high performance yet. But 100 kilojoules, that meant that the energy deposition by the alpha particles was higher than the initial energy coupled from the laser into the hotspot. So that was an important milestone. In August 21, we did the first experiment where we exceeded the Lawson criterion of ignition. This is this attempt in physically meaningful terms to define the proximity to ignition using pressure, temperature, and confinement time. So in terms of the physics, we got ignition at this point, but it's not a very intuitive way to define ignition. So most people think about it as break-even, where you get more energy out than you put in. That's the definition by the Academy of Sciences, and that's the definition we're using at the lab as well. And we finally got to that milestone in December 2022.
This is not the question, but how much electrical energy does it take to get a joule of laser energy?
300 megajoules. I will get to that. 300 to 400. So it's important to point out that the I'm sorry, there was no.
Sorry. I just wanted to, you might have said this, I apologize. How does this compare to ITER?
So ITER is a magnetic confinement facility. So it's a different approach. It's what I showed earlier. And again, I don't know very much about it. I will say though that ITER is probably about 10 years away from demonstrating ignition in experiments because it's not even finished construction yet, and they haven't started shooting, well, they won't start shooting deuterium-tritium until I think the early 30s. I may be wrong with this. But so there's still some ways to go for ITER. I do think they will get there though. I mean, don't get me wrong.
Just out of curiosity, you see you have comprehensive test entry.
So NIF has many missions. So we don't only do ICF experiments, we do many other things as well, such as stockpile stewardship and national security applications. So there's sort of there's a longer answer to that. But basically, the world as a whole decided that blowing up nuclear weapons all the time is probably a bad idea, so we should stop doing that. But now we have a problem because we somehow need the expertise alive to maintain our nuclear stockpile and also to make sure that the role it plays in terms of deterrence still exists, right? If we have a nuclear stockpile but we can't be sure that it works, then it's not a very good deterrent. And so we needed something else to keep the expertise alive, and the work that we're doing on the NIF is very much directly related to that. Okay, so that's some of the work we're doing, but we're also doing a lot of fundamental science. So we're doing things like nuclear synthesis or laboratory astrophysics at the lab as well. And also, it turns out NIF makes for a very good backdrop in science fiction movies. It was used as the warp core in Star Trek Into Darkness. And so here's actually a screenshot from the movie. The blue thing here in the background, that's the target chamber. These structures at the top are beam paths. There's some diagnostics in the background as well. As someone who actually works there, this is a very stressful movie to watch. They're running around, they're touching things. Things are exploding. But it's fun.
Hopefully, Livermore got a lot of money for being.
Well, they certainly got a lot of PR for it, which it's difficult to express in money, right? Okay, so let's talk about NIF a little bit more. NIF is the world's most energetic laser. I've mentioned this before. It's also the largest optical instrument ever built. It contains well over 30,000 optics with a combined area of 3,000 square meters. That's about 30,000 square feet. It's very big. It's the size of it's the size of 3 football fields, and it's 10 stories high. I recently watched the Taylor Swift Eras concert movie with my daughter. I was in the SoFi Arena in LA. This is about half the size of that arena, sort of as a frame of reference. If you take the roof off, you'll see that most of the building is laser amplifiers. There are 2 main laser bays, with the amplifiers for half of the beams each, and then the beams are directed to the target chamber, which sits here at the bottom right of that picture. And then the energy that we take off the grid, the 300-ish megajoules, is stored in capacitor banks on either side of the facility. So the laser just operates off of the grid. Energy is stored in these capacitor banks, and then we can shoot. I think technically up to every 8 hours we can fire this. In reality, depending on how complicated an experiment is, it might be several days for a single shot. Okay, so with those 300 megajoules, we generate 3 megajoules of infrared laser light. So this is about 1 micron wavelength. But then for physics reasons, we actually don't like to shoot in the IR, so we frequency triple it to UV, 351 nanometers, and that leaves us with about 2 megajoules of laser light that can be put on the target, and a typical pulse shape is shown here at the center. These are very carefully shaped pulse shapes, and so this is total power as a function of time here. And I should point out that NIF was not built for efficiency. It's a research facility. It was built in the 90s with technology that was already robust back then. We just made it bigger, and the word just does a lot of heavy lifting here. But it's essentially decades old technology at this point. If you were to build something like this today, it would have a much, much smaller footprint, and it would probably be about 10 times more efficient.
10 times more efficient, meaning if the 300 megajoules, you need about 30 megajoules
Yes.
to make 2.
Correct. Yeah. So the 2 megajoules of UV light gets converted into X-rays. Of that, only about 250 kilojoules actually make it into the capsule, the target at the center, and then that capsule again is this 2 millimeter diameter sphere that gets imploded roughly to the size of a human hair, about 100 microns wide, and in the end only about 20 kilojoules are actually contained in this small spot. And so I find the scales here really fascinating, right? You have 150,000 square feet facility to generate something the width of a human hair, and you couple, a tiny fraction of a % of the energy into this tiny spot here. But that's what's needed to get to the conditions for a sustained fusion reaction. Yes, please.
I'm so sorry, I have to ask.
No.
What's the price tag on this?
So the facility itself, I think, cost about $3.5 billion, which I don't know what that is in today's money. Billion. B. The SoFi Stadium cost $5 billion. I looked that up this morning. So so the scales are really. Yes.
What the heck is in the stadium then?
What's that?
What is in the stadium that would cost that much?
I don't know. Big screens. I have no idea. Okay. So let's talk a little bit about the target because I think these are really marvels of engineering. They require state-of-the-art microfabrication precision and cryogenic operation. I will tell you why we use cryogenic targets in a bit. But here's a picture of one of the targets that we would actually shoot. This is the cylinder, about 1 centimeter by 6 millimeters in size. It's made out of gold-lined uranium, to your question earlier. You have these arms here at the top and at the bottom. These are cooling arms. They control the temperature profile in the target. The wires coming off of various temperature and pressure sensors. And then there's holes in there. These are diagnostics windows, so we can actually look inside. And then we have a little jacket here that contains the fill tube. And the fill tube is connected to the capsule at the very center, and that's how the DT fuel actually makes it to the capsule itself. The capsule is this 2 millimeter diameter ball that sits at the center here. And according to our target fab lead, who admittedly might be a little bit biased, this is one of the most perfectly engineered things in the world. It's almost perfectly round to within a fraction of a micron, a small fraction of a micron. And it's the surface smoothness is, it says 10 nanometers here, it's actually usually better than that. And just to put that in perspective, if you were to blow this up to the size of the Earth, the biggest elevation difference between the deepest sea and the highest mountain would be about 200 feet. So that's how smooth these things are. It's made out of high density carbon, so that's artificial diamond. The reason it has to be this smooth is because we really care about perturbations. Any ripple on there, any flake or anything like that, if you compress it by a factor of 20, as we do, these things get amplified by orders of magnitude, and that can be really disruptive to the implosion. It can introduce mix to the fuel. It can, in the worst case, actually rip up the capsule in flight, and then you lose all the confinement, and so your experiment doesn't work. So that's why these things have to be as perfect. Another picture of the target here. This is an X-ray radiograph. This is how we characterize these targets and metrologize them. The outside layer that you're seeing here, that's the carbon ablator. Then there's a dark ring that's also carbon ablator, but it's doped with tungsten, and we use that to control how X-rays can penetrate these targets. And we use it to stop preheat of the fuel on the inside because we keep it very cold so that it's easier to compress. Something as cold is easier to compress. If it was a warm temperature, a room temperature target, we would need a lot more laser energy to get to the densities that we require in the end. So that's why they're at cryogenic temperatures. And at these temperatures, 19 Kelvin, the DT actually forms an ice layer. And so that's the innermost ring here. It's a thin 85 micron ice layer that adheres to 85, something like that, that adheres to the inside surface of this target here.
Sorry, this is the...
This is the capsule. This is that again, but it's
So the DT is on the inside of this?
Yeah. So the capsule itself is made out of carbon, and then we have a small fill tube here that you can barely see in the zoomed in version. That's how the DT gas gets in there. And then it takes about 3 days to form this ice layer, because that also has to be pretty much perfect. It's basically, that's basically a single crystal ice layer here. And again, any grooves, any imperfections here can be amplified many, many times when you implode this, and that's why this has to be as good.
And that overrun, that survived?
No.
No, that doesn't.
No, everything is gone after you shoot. Yeah. And I should point out that all of these targets are basically hand-built. So we don't have an automated process for this because we change things, right? It's experiments, you want to scan different things. And so there are actually people there building this. It takes a long time. As someone who's very bad at Jenga, it amazes me that we can do this. All right. Okay, so now we're going to watch a quick movie as to how an experiment might unfold. Let's see. So we're going to start, this is the NIF building in sunny California, and we're going to start our movie in the main control room. This is set up like a NASA control room, so we have a shot director as well as various substations where operators take care of individual aspects of the experiment, such as laser or diagnostics. And then when you press fire, the first thing that happens is that the capacitor banks discharge into the laser base, and so you charge up the amplifiers, and so now they're ready for the laser to come to appear. The laser is actually born in the master oscillator room, that's what it's called, and it's born at the picojoule level, then it's shaped at the nanojoule level very carefully. We can actually have up to 48 different pulse shapes on an experiment, and so half of these pulses then get sent into each laser bay, so 24 on either side. They then go into the preamplifiers, where they amplified about 10 billion times to the 10 joule level. And then they exit the preamplifiers, they get split 4 more times, and so now you have 96 beams in each laser bay. And then they go to the main amplifiers, where they bounce back and forth 4 times to get to their final energy in the infrared of 20 kilojoules per beam. And at that point, the laser is about 1.5 square feet in size, so each beam it goes into what we call the switch yard, where it's then directed to the target chamber, half to the top and half to the bottom. And as it enters the target chamber, it goes through conversion crystals to generate the UV light. And so now you have about 2 megajoules of UV laser light that actually enters the target. And then you know the rest. Oh, shoot. By making it big. So to keep the fluence at a level where it doesn't damage the crystal, that's why you have 1.5 square feet of beam size, yeah.
What's the laser material? Are you allowed to tell us that?
I'm allowed, it's published, but I don't know. Well, I guess, the laser is, I think, it's a glass laser. It's an Nd:YAG, I think. What the crystals, the conversion crystals, I thought you were asking about the conversion crystals, because that I don't know. Yeah. Yes. Okay, so anyway, the laser enters the target, it heats it up, it creates an X-ray oven, and if you get it right, you create a little star at the center of your chamber. Mm-hmm. And then, of course, because we are a research facility, we generate gigabytes of data on any experiment, and so that data then gets sent to the main control room, where it's then archived for further processing. All right, and I mentioned some of these experiments may take a while, so if you have a complicated experiment, you end up spending a lot of time in a dark room without any windows. So after the shot, you get to go outside and enjoy the California sun. We operate 24/7. No, we operate 24/7, so we shoot when it's ready, yeah. Okay. All right, so now you know all the background, so I'm going to talk a little bit about the history. I'm not sure how good my time is with the questions, but please do ask questions. I think it's important that everybody understands. Okay, so I'm going to talk a little bit about the history and why it took us such a long time to get to this point. So a key requirement for a sustained reaction is that energy losses are balanced by energy gains, right? That's fundamentally a requirement for any reaction that you want to have sustained. So in this cartoon here, we now assume that the target is fully assembled, so it's imploded all the way in, doesn't go any further. We have a hotspot at the center that is surrounded by our very dense fuel, and so the hotspot now launches some fusion reactions and it creates alpha particles which are stopped in the ice, or in the, well, it's probably not ice anymore at that point, but it's stopped in the dense fuel, and that's our energy source, right? That's what keeps the heat on. The losses come mainly from two things. One is the expansion PDV. I mentioned this earlier. Once this thing is fully compressed, it doesn't want to be hot and dense, it wants to explode again. And that fundamentally puts a limit as to how long you have to do this. So you have a confinement time of about 100 picoseconds. And once it expands, you lose pressure, you lose temperature very quickly, so the whole thing stops. The other loss you have is from Bremsstrahlung, because this thing is, of course, very hot, hence the name, it's a hotspot. And any amount of mix that you introduce, anything that is not deuterium or tritium, will radiate even more because it goes with Z squared. So that very quickly puts a stop to your reaction. And so fundamentally, this is expressed, this energy balance is expressed as the Lawson criterion, which is this pressure times confinement time as a function of temperature. So it's here written, or it's here shown for inertial confinement fusion. You can do the same exercise for magnetic confinement. Basically, this black line, that's what delineates the two regimes. So on the left-hand side, which is where we spent most of our time in the last couple of decades, the losses dominate, and on the right-hand side, the deposition from alpha particles dominates. So that's where you want to be. And so why do we not get to that side? Well, there's many degradation mechanisms, but we found that over the last 3 years, there were really three main ones that we had to worry about. One is mix, and then there are various drive asymmetries. And so the mix comes from any perturbation on the capsule. The fill tube is a perturbation. There may be imperfections in the capsule. So I told you earlier that these are smooth to 10 nanometers. Unfortunately, that's not the whole truth, because there will be pits on there will be voids in the walls of the capsule itself. Sometimes there are high Z inclusions, so materials you don't want to be there. Maybe some of the tungsten isn't quite in the right place. And so all of these things are problems. And we metrologize these targets very carefully. We know exactly where the pits are, where they're located, how many there are, and then we pick the targets we want for our experiments. And so in reality, that means maybe a third or maybe 2/3 of the capsules that are being made are never actually being shot because they're simply not good enough. Then other sources of asymmetries are just drive asymmetries. So in this picture here, you can imagine the laser beams on the right-hand side are a little bit hotter than on the left, or maybe the losses are a bit higher on the left-hand side because you have a diagnostics window there. And that means you're pushing your entire capsule, your entire target to the side a little bit. And we see this quite a lot. We see velocities of up to 100 kilometers per second, which if you consider that the implosion velocity is 400 kilometers per second, that's a substantial amount of kinetic energy that you're not using to heat and compress your fuel, right? That's energy you leave on the table. And then you can just basically imagine going to higher modes. So mode 2 asymmetry is if you have your laser beams, for example, a little bit hotter towards the laser entrance holes than on the waist. That means you're pushing a bit more from the poles. You're creating an oblate implosion. The technical jargon we use for that is pancake. And so it basically becomes flat. And likewise, if you push a bit more from the equator than from the poles, you create what we call a sausage or a prolate implosion. And again, you'd leave kinetic energy on the table. You're not doing a very good job at compressing it efficiently. And here on the right-hand side is actually some experimental data where we did a power balance scan. And so you can see this sort of goes from flattish to roundish to elongated. And there are other things that we worry about, but these three tend to dominate our energy losses, our efficiency losses. And the way we diagnose this is, of course, with diagnostics, fundamental to any good experiment. But it's important to realize that we cannot shoot these experiments very often. These high-yield attempts at lighting up a star, we shoot every couple of weeks. We want to make changes to the design. So a specific measurement for a given design, you may not ever get more than 2 data points. And so it's absolutely vital that we get the best quality data we can on any given experiment. It's also worth considering that this is a very hostile environment. It's over in 100 picoseconds. It's at the center of a 10-meter vacuum chamber. It's very small. It's 100 microns in size. There's a lot of EMP, a lot of neutron and X-ray radiation. So all our diagnostics are basically purpose-built. We have a whole part of our program that is dedicated to designing, building, and maintaining diagnostics, as well as anticipating future needs. And in total, we have about 120 diagnostics that are available for internal and external users. There's no distinction there. And with those diagnostics, and you may field something like 40 on a given experiment, so we don't field all of them at the same time. But these diagnostics then tell us about input conditions, the shocks that we launch into the target, maybe the Hohlraum temperature profile. It tells us about stagnation properties, such as fuel uniformity or maybe the hotspot shape. We look at spectral signatures in the X-ray emission. It tells us about mix in the hotspot. We look at temporal profiles. It tells us about time of peak emission in the X-rays or the neutrons. And then, of course, we can do many of these measurements from multiple directions, so we can reconstruct the 3D properties of our experiment that way. Yes, please. You're asking all the questions. It's great.
To be fair, I wanted to meet you and because I was teaching today, so I can using this too. Questions too. Sorry to use some completely different, but I was wondering from a term of an operation point of view. Is it kind of like CERN, where CERN you got have some free time and then there's extensive period of maintenance, upgrades, etc., where you don't do anything? Or is this kind of like, I'm having, considering the size of the facility, I'm having a hard time understanding kind of like the, how do you take your data? Like I understand what you're doing, but...
So there's an army of people enabling all of this, right? We have many people that are experts in specific diagnostics. And so if you design an experiment, you're really ultimately filling out a spreadsheet and you're saying, this is what I want. I want this laser on this beam, blah, blah, blah. And then other people do it for you. And then, so there's a lot of setup that happens in the background in between experiments. As I mentioned, we operate 24 hours a day. And there's a shot schedule for the week that says between these hours we will do that experiment. That target will be fielded and we're getting the laser ready, and then you get your shot and then it's someone else's time on the facility. But we shoot, there's regular maintenance periods on the weekend. There's 1 day of maintenance. And then there are extended periods of maintenance where you have, like, for 6 weeks, you don't have a single experiment. But all of that is scheduled out for the year. But we ultimately, in terms of experiments, we really operate 24 hours a day. And yeah, you don't have to set up these diagnostics. In fact, they don't want you anywhere near them. There are experts who know better than you. Okay, so with this knowledge, now we can go on a little bit of history here. So this plot will be evolving in time. This is a plot of about 800 experiments that we did since 2010. All of the DT experiments, all of the attempts that we had on lighting up a star in our experiments. And so this is here target gain as a function of time. Each bar, so this plot will be populated with bar. Each bar is one experiment. They will change colors, don't worry about that. This is different experimental platforms that we tried. It's not relevant for this talk. But notice that the target gain here, we're starting at less than 0.1% efficiency, and we want to get to 1. That's the goal. All right, so in 2011, or actually late 2010, I think, we did our first experiments, our first DT shots, and they really didn't perform very well. These targets used CH ablator, so plastic as an ablator material. And that has historic reasons. There were many years of experiments on how to learn to do these implosions with plastic ablators rather than the HTC we're using today. But it didn't perform very well. There were fundamental limits to the symmetry that we had. We had a lot of laser-plasma interactions, where that's how the laser interacts with the plasma inside the Hohlraum. It gives rise to hot electrons, to backscattered light, things like that. So it really wasn't a great environment. And at the time, people somewhat correctly judged us for enthusiastically calling the facility the National Ignition Facility. They said it should have been the near ignition or never ignition facility. But yeah, worked out in the end. So in 2013, we made a change to the design. We changed we used the so-called high foot design. The foot is the very front part of the pulse shape that is shown here. And it basically controls the stability of the implosion. And so by increasing that, you're increasing the adiabat. You're increasing stability at the cost of compression, but it actually worked out. We got an increase of about a factor of 10 in yield, so we're now at around 1% of 1.5% of efficiency. target gain, but ultimately we were limited by the same issues as we had before because we didn't address any of the underlying issues. So in 2016, we made a fundamental change to the design. We switched to high-density carbon, which is the ablator material we are still using today. This, in hindsight, was the right thing to do, but at the time it was a very radical change because, again, there were years and years of experience on how to do CH. There were years of experience on how to do high-quality targets with CH. So changing that meant we really had to learn how to walk again. But it looked very promising very quickly. We got a factor of 2 or so in improvement there. But then found when we tried to push this even harder, go to higher compression, we're sort of banging our head against the walls here. And we found that we were fundamentally limited by the quality of the targets themselves. And so that started a concerted effort into improving the quality. That's things like pits and inclusions in the targets, which then also looked very promising. And so in late 2020, early 2021, we got the first experiments where we had a burning plasma. And so now the energy deposition by the alpha particles was higher than the energy initially coupled to the hotspot. And so that meant you're getting to a point where the fuel density is high enough and you're really getting, things are heating up. Okay, so we then made a change to the Horam design. We tried to couple more energy to the capsule by changing the aspect ratio between the capsule and the Horam and a few other things, and that worked out very quickly as well. We got to a target gain of 0.7 here in August 2021. And you'll notice that there are very sudden jumps here in performance, and that's because this is such a dynamic system. Because when it gets going, it really gets going, and that's why you see very large fluctuations here in the performance. So a small improvement can have a very large impact here. With a target gain of 0.7, it feels like you're so close, and there was a lot of feeling like, well, let's just repeat it a couple of times. We just have to get lucky, and we'll get to a target gain of 1. Turns out that didn't work so well. And really that August 21 shots, that was the lucky shot where things sort of aligned the right way. Most of the repeats here underperformed, and we were still limited by target quality at that point. And so in parallel, we were working on increasing the available laser energy on the facility. So all of these shots here were at 1.9 megajoules, and we increased that to just over 2 megajoules, which isn't a lot, 2.05, 150 kilojoules more. But it allowed us to thicken up the shell a little bit and just become a little bit more robust to perturbations. And that then paid off very, very quickly. And we got to this result here of a target gain of 1.5, which is the reason I'm here today.
So what did you do to get to more stable?
So you have perturbations growing on the capsule from, things like a flake landing on, something, or pits, right? And so if you make it really, really thick, then you don't care about that perturbation because it never reaches your hotspot. So if by having more laser energy available, you can thicken up your capsule without compromising on the implosion velocity and the kinetic energy you can impart on the capsule. And so that allows you to just be a little bit more robust to these perturbations. And it turns out that, because you're in such a dynamic regime where small changes make such a huge difference, that turns out to be, the element that helped us get over the edge.
What happened after?
I'll get to that in a second. Okay, so just to put this in perspective, this is again your Lawson criterion plot, pressure times confinement time as a function of temperature. All of the experiments that I showed you were on the left-hand side of this curve, and then more recently we managed to get to the right of this curve. So this is that December 05 shot from last year. Okay, and then when we did that experiment, people asked when are you going to do it again, or if they were less kind, they said, do you know what you're doing? Oh, hello, what happened here? And that's done. That's the talk. Here we go. And so this is now target gain again as a function of time for all the DT experiments that we've done since August 21. So here's our first ignition result. And then these are the most recent shots. So all of the shots are on here, and you can see that basically all the shots in the past have gotten to a gain of 1 or higher. We actually set a new yield record in late July with a gain of 1.9. So that's currently the record. We actually tried a few different things here. So this October 7th shot here tried a slight change to the design, but went back to 1.9 megajoules laser energy. So it's really directly comparable to this shot here. And with a very small change, we managed to double the performance here, almost double the performance, not quite. So we're working on a couple of different things to try and improve the performance further.
Can you eventually get a gain of 20?
Oh yeah, absolutely, yeah. So yes, you can. There is no limit. There is fundamentally you can just make it bigger, and that will scale very favorably. Just everything, make everything bigger, make the laser bigger, make the capsule bigger, make the and it's trying not to say the wrong thing here. I think it scales it with a fourth power of scale. The yield scales with a fourth power of the scale. Yeah, so doubling the diameter will be a factor of 16 in performance. Yeah. So it's a thin shell, high density carbon shell of about a few tens of microns. On the inside of that is the DT, because it's cryogenic. It's a layer of ice, and then the center of that is sort of the vapor pressure of the ice. So it's not a vacuum, because some of the DT will still be in gas form. You can make the ice thicker, and there's reasons why you might want to do that. It also makes you more stable to perturbations and things like that. But you always have to pay a price. If you make it bigger, that means you have more mass, you have more payload, which means your implosion velocity is going to be slower. And the implosion velocity is ultimately the thing that you need to get very high pressures and density. So if you make it too slow, you can never get to the point where you get enough temperature in the hot spot and enough density in your fuel. So there's always a balance. Okay. All right, so that sort of brings us to today, which brings us to what are we going to do now? So one of the key motivations behind this, and maybe that's something that should have been in the introduction, is that fusion energy may be the ultimate clean and limitless energy source. That's one of the key motivations behind doing all of this work. And it's really worth pointing this out because people get scared about nuclear energy. It's fundamentally safe. So in a nuclear fission reactor, your fuel rods last anywhere between 5 to 10 years. In this, because it's this small fusion capsule that only lasts for 100 picoseconds, the amount of fuel in there is fundamentally limited, and it's such finely tuned that if you do any perturbation to it, it will immediately stop. And then if you just don't put another target in there, it will stop, right? In a fission reactor, you control the energy output by moderating it. And if that moderator fails, like in Chernobyl, then you get a runaway reaction. That's fundamentally not possible here. It's also carbon-free, which is something we should worry about. It's also sustainable. So the two key ingredients here are deuterium and tritium, and I was corrected today. I used to say that deuterium is one of the most common, the most abundant isotopes in the world. It's one of the most abundant radioactive isotopes in the world, so thank you for that. But every 1 in 5,000 hydrogen atoms is a deuterium, so we have plenty of it in the sea. Tritium itself does not naturally occur. It has a half-life of 12 days, but we know how to make it, and it can actually be part of an integrated fuel cycle in a fusion reactor. So we know how to do that. And so potentially that provides energy independence. You don't have to source your fuel from somewhere else in the world. And of course, that's one of the main reasons why the US is interested in that, because there's significant strategic advantage in having abundant, safe, and independent energy, right? Having energy security in the country. And then another point is you don't have a problem with long-term storage. You're not creating any radioactive isotopes that are around for tens of thousands of years. Of course, your target chamber, it's being bombarded with neutrons in a reactor. It will become activated, but the half-lives of that are much, much shorter than anything you have to worry about in a nuclear fission reactor. So, we're not talking about hundreds of generations here. So it's a lot more manageable. So how would a fusion reactor look like? The front end would be something like NIF. You need some sort of big driver to implode your target. So, something like NIF, a big laser. But the difference is, rather than shooting it every 8 hours, which is what NIF can do, you now need to shoot it about 10 times a second. And then the gain you need in an implosion is about 100. Currently, we have a factor of 2. So there are some ways to go here, although there are ideas of how to go about this. But with that, 10 times a second, gain of 100, you get about a gigawatt of power. That's a pretty good number for a modern power plant. And then you line the target chamber with lithium. That does 2 things. One is it breeds tritium, and so that's part of your closed fuel cycle. And the other one, it heats up the lithium, and then you use that in a heat exchange to ultimately boil water and drive a turbine, which I always find funny. That's how every reactor works today, right? But we capture the essence of the sun, the most advanced technology we have, and then we use it to boil water, which is what we did 800,000 years ago.
James Watt will be smiling somewhere.
Yes. So it's, but this is not something we can do today. There are significant technological hurdles to overcome here. Again, we need something that is high gain. We need a high efficiency, high rep rate laser. Both of these things are something we work on very actively in the lab. But then fundamentally also your target production, the production has to be automated and it has to become much cheaper. Right now, these targets take months because you're growing the HTC and then you're hand assembling them. So this is a very, very long process. This has to be completely automated and it has to be very cheap because you're shooting 1 million targets a day. And then, of course, you need something that can withstand this neutron environment because you want to operate your facility for many, many years. So this is not something we can do today, but there's ideas out there on how to do it. And the way I like to think about it is in terms of the Wright brothers moment, when in 1903 they demonstrated flight for the first time, they managed to go 100 feet, which is completely useless, right? I can throw about as far. But it was the implication of that changed the world and changed society. And I think that's where we are today. And as a side note, I think we have the 120th anniversary coming up on December 17th in 3 weeks for the Wright brothers moment. So I've looked that up this morning. All right, so I think that's where we are. There is considerable interest in this in the private space. There are a lot of fusion startups. There are about 40 companies working on fusion ignition today for commercializing fusion ignition for energy production. And there's a lot of money in this. As of July 2023, the total investment was something over $6 billion in this space. Most of that is in the magnetic fusion area, but a lot of the companies that were formed in the last couple of years are working on inertial confinement fusion, and that's directly in response to the results that we have been publishing. And just to put sort of a perspective on this, and I'm not sure this is entirely correct, but by my calculations, building the NIF and running the facility for 10 years and having the ICF program for 10 years cost about $7 billion-ish, roundabout. So this is a lot of money, $6 billion. Okay, so to facilitate or to leverage the expertise and knowledge that we have at the lab, we actually started an IFE collaboratory together with to facilitate partnerships with private companies. And so these are the labs that are participating in this. And we're working with a number of private industry partners on developing the technology that is necessary to commercialize fusion or to use it as a power plant. I don't know that much about it. If you squint really hard, you'll see I am not in this picture. So I'm wrapping up my talk here, just talking a little bit about what's coming up for NIF. So this slide is a bit outdated by now, but the goal for FY23 was that we wanted to demonstrate routine megajoule operations and ignition. I think we've done that. I showed that on a previous slide. We also were working on increasing the available laser energy to 2.2 megajoules. Until recently, it was limited to 2.05. We actually missed that milestone for FY23, but we did demonstrate that a few weeks ago in an on-target experiment. And we're going to try that again with a DT implosion in January, I think. So maybe we'll get another yield record then. Over the next 5 years, the focus at the facility is going to be on long-term sustainment as well as increasing the capability further. Long-term sustainment because it is an old facility. at this point. It's well into its second decade of operations, so it's starting to show its age and it needs a bit of TLC. In the meantime, we're using this opportunity to push the capabilities up further. So there are plans to increase the available laser energy to 2.6 megajoules, possibly even 3 megajoules on target. And with that, we think we can get to tens of megajoules of yield. So now we're talking gains of about 10, maybe 15 or so. And then beyond that, in the 2030 to 2040 timeframe, we're hoping to explore designs that give maybe 100 plus megajoules in yield. Obviously leveraging the increased capabilities that we've been working on, but also the expertise that we've gained over a couple of decades of experiment. Yeah.
So in this, the external energy or the wall socket energy is about 30 to 40. That's remaining constant as you're going along, or is that increasing?
It's 300 to 400.
Sorry,
Yes.
300 to 400.
Yes, yeah.
But you mentioned that if you use new technology, that number will increase.
Well, but that's fundamentally changing the laser itself. So you're not using a flash lamp system, you're using a diode pump system, for example. But NIF, fundamentally NIF isn't going to change. Right? It's still going to be the same laser.
This is 3 to 400 megajoules, and you're still getting 100 plus.
Well, not at this point, but yes.
No, that's the goal.
That's the goal, yes. Yeah. I have to say, so I didn't put the slide together here. I'm a bit skeptical about this number because it would require, it's not impossible, but it would require upgrades to the shielding that we have in the facility. Right now, the facility is not rated to 100 megajoules of nuclear yield. So if we get that, we would shut down right now. Because that becomes a safety issue. Yes?
I was wondering, because I'm having a on picture in my head, I was wondering how commercialization, like what do you think commercialization would be like? Like how would it go about it? Are we just going to start like building fusion reactors the same way that we have, like nuclear reactors? I think that's how we're planning to do it. Is there something else to it?
Not really. I mean, it's, you build the thing, you drive a turbine, and then you provide energy to the grid, right? That's the idea. Obviously, that's a bit, very simplified at this point, but ultimately that's the goal. Yeah. I don't know if did I address your concern there, or?
No, it's not a concern. It's really just wondering what the landscape would look like, 10 years or 2 years.
Everything is better. So again, I mean, this is, there are significant hurdles to overcome to get there. And there's a lot of money in the private space to work on this. And I think some of the concepts that are being proposed by private industry are more realistic than others. But ultimately, they have to deal with a lot of the fundamentally the same issues. Things like rep rate driver, things like injecting a target at high rep rate so you can actually shoot this every 10 seconds or so. And so they all share these problems. And so even though maybe the end product that they're delivering may not look like what they're currently selling, it will help the entire space. The investments that we have and the technology that's being developed, because everybody sort of has to build on the same fundamentals right now. And there's a lot of money in this, right? If you can commercialize this, you're basically printing money.
Well, I thought the idea was free electricity.
Yeah, maybe.
Just the free electricity that you can sell.
That's right. Okay. So I think let me just wrap this up really quickly because I am at the end here, and then we can go into the discussion. So just want to highlight again that this really was an accomplishment built on several decades of work by the community, and the community really spans a lot of places. So this map here shows places in the US, companies and labs that we've collaborated with, but it's really an international effort. We've worked with CEA in France, with AWE in the UK. We work with private partners in Germany and other countries. So it's a very big effort. It's not just Lawrence Livermore National Lab. There are many people involved in this. And this is my final slide, but one more thing I want to say, if you have graduate students or undergraduate students that might be interested in working at the lab, we do have a very active summer student program. So if you want to come out for a few weeks and do some science with us, like these are real projects, and get paid for it, then please do apply. Thank you very much.
So we have about 10 minutes for questions, so please fire away.
Yeah, so on that slide you were showing us the projection. This one, yeah. So even by 2040, it's not viable in the sense you're still putting 300 megajoules and getting 100 megajoules.
Well, yes, but this is with NIF. NIF is an inefficient system. It's a research facility. It's not built for efficiency.
But that's what I was asking. So that means if you build an efficient system, then the input would be like 30 or 40 megajoules.
Yeah, sure, yeah.
And you'll be getting 100 of it.
Well, you know, yeah.
Yeah, whatever. Something.
Whatever, yeah. So, yeah.
You might get true.
Yeah, wall plot break even, as people call it, yes. Yeah.
Okay.
I think there are also significant innovations in what you can do to convert heat to electricity
I see,
without
yeah.
boiling water. Yeah.
Yeah. And so I should also point out, the lab has a very particular interest in this work, right? We're a national security lab, so there are specific applications that are envisioned for this. So the using this as a source for energy is certainly something that is that people are very excited about, and it's something that, you know, the administration and the DOE want us to be working on, but that's not the main things we're interested in the lab. And so a design that you want to use for power production would probably look different than these targets. So for example, we use this ice layer that we grow over several days, and it needs to be nearly perfect, right? You can't do that in a commercial fusion reactor because you want to shoot this every 10 seconds. And if you have to grow a layer and store enough targets that you can operate for a couple of days, then you have a radiation problem because the amount of tritium you need to have is just too much, right? So you need to be able to do this layer very, very rapidly. And so there are ideas out there, for example, about wetted foam. So having a very, very low density foam, something like 20 milligrams per cc or so on the inside. And so then the liquid DT gets injected and it wicks to the foam and it forms this layer. And that's something you can do in an instant, essentially. So things like that. But that's very much something that is interesting for the fusion energy space and not necessarily as interesting for us. Yes.
My question is related to the parent path. Actually, what other options are there for turning the power into practical other than boiling water and turning the turbine? What is a better option? I'll give you an example.
Well, I mean, again, that's how power plants work today, right?
Yes.
So, I mean, I don't think we've figured out a better way than the, you know, the, what's it called, the Carnot cycle, or it's
Always the product, right?
What's that?
Heat is the product.
Yeah, that's right.
You have to convert heat.
Yes, right, that's right. So that's the product. See, yeah, you're right.
Is there any, do you know, have a significant work in sound fusion?
Say that again?
Sonoluminescence based.
I've heard of it. I'm not aware of what's going on in that area. I know what you're talking about, but
do you know if there's any significant funding or research going on there?
I'm not aware of anything. No.
When you were talking about the timeline of the game that you had from 2011 to 2022, right? There was a time when you said that we actually started to use high density parts. And before, earlier in the talk, you said that there are many reasons. Can you tell me one or two? You might have told them like.
So one of the main things we found is that so the time scale of the experiment is, Actually, I'm not going to go back to that slide. The timescale of the experiment is fundamentally set by how quickly the shocks propagate through the target, right? Because that ultimately, that's the information, and that sets how quickly you can start the implosion, and that's how quickly things move.
So, diamond is high.
Yes, and so diamond has a higher density, which means the shocks propagate faster, and that means you're shrinking the timescale down significantly. And that allows you to do a couple of things. It means so the other thing you're dealing with is as the laser is focused onto the inside wall of your cylinder, that thing becomes a plasma as well. And so it starts moving in. And that means at some point you lose shape control of your capsule implosion because the laser beams can't get to the point anymore where they need to go because the plasma density is above critical for the laser. And so by being able to, so you can control this with a gas fill, so we're really going into the depths of this design here. You can control the rate at which the wall plasma expands by putting in a low density gas fill into the hole round, so it's not a vacuum. But that creates other problem because now your incoming laser is interacting with gas all the way to the wall, and that creates backscattered light, that creates hot electrons, all things you don't want. And so by shortening the time scale of your implosion, you can lower the density because you can let the wall expand faster because you don't care about it anymore after 10 nanoseconds, whereas before you had to keep it back for 25 nanoseconds. And so that means you lower the gas density, that means there's less laser interaction with the gas, and so you win on many fronts here.
So if there was some material that had higher than your
well, I mean, there's also the manufacturing problem, right? So in terms of, for example, in terms of absorption efficiency, beryllium would probably be better, but it's very, very hard to make a high quality beryllium shell. And it's also not very nice to deal with. You're absolutely right, yeah.
What is the software simulation suite like, and like how fast from having like I don't think part of it, something like a simulation suite to actually
I mean, we have many different software tools available. Many of the codes we're using are internally developed hydrodynamics codes, and they go from very simple 1D that you can run on your machine in a matter of seconds up to 3D simulations that take sort of the greatest and best ideas and use supercomputers and run for weeks. So we have everything, and then recently we've been also working on AI models that are sort of trained on simulation data to allow us to increase the parameter space. So you have discrete simulations at different points in the parameter space, and then these machine learning approaches allow you to fill in the gaps. So there's basically every tool there is available we will use.
If you have a new idea to test like the whole setup, you simulate it pretty obviously.
Oh yes, yeah. I mean, that depends. Depends if you can convince the right people. So there may be, anywhere from, it won't happen in a month because the schedule is laid out for a year and we have proposal rounds that run on a yearly cycle. But the feedback may be, hey, you want to test some of the fundamental questions first on a smaller facility where you can get 10 shots a day rather than one in a month or so. There was another question. No, the capsule isn't uranium. The wall of the cylinder is uranium. And that's because we are trying to generate as many X-rays as possible. And so the laser, right, we use the laser to create this X-ray oven that then implodes the target. And high-Z materials are better at converting the laser energy into X-rays than low-Z materials. And so you want to use a high-Z material to do that. And the best, the highest solid material you can work with is uranium. So that's what we do. But uranium takes on water, so that's a problem, and other impurities. So we cover it in gold, which is sort of the next best thing. In a commercial target, you wouldn't use that because that's very expensive, but you could use something like lead. So there are designs for lead hole rounds.
specifically asking that why don't you use the shape other than for the gas?
I can't see how that would be more efficient if you want to maximize the amount of. Yeah. But if you imagine, so I didn't quite hear what you said, but I want to make one more comment. If you're not compressing it symmetrically, then you will have some sort of weak spot in your confinement, and that means everything will sort of go that way, and then you don't have confinement.
That's one of the modes of failure you kind of show that it just squishes.
Yeah, exactly. Yeah. So, and you had a question there. I cut you off.
I just think that, but I think your answer is better. That's the thing. But I would think that sphere also maximizes the volume ratio. So that might be one thing.
Yeah. No, that's a very good point.
This would be a very nice question.
No, that's.
Why do you need to generate X-rays? Why can't you just have laser beams coming?
Okay, so that's a good point. There are different approaches to inertial confinement fusion. There is what we call direct drive ICF, where you put the laser directly onto the capsule, and then there's indirect drive. Both have advantages and disadvantages. The advantage of direct drive is you don't have this intermediate step, so you can potentially couple a lot more energy into the target. It also makes the target fundamentally easier, and so a lot of the commercial ideas use direct drive designs. However, you now have a problem with asymmetry, and so both low modes and high modes. So the advantage of the Horum is that it smooths out the drive profile immensely. So essentially the capsule just sees a sky of X-rays. It doesn't see individual drives, it just sees a sky. And that's fundamentally smooth, which is why we care sort of about mode 1, mode 2, maybe mode 4. But beyond that, we don't really care about that much because the Horum does the work for us. It makes us smooth. If you do direct drive, that's not the case anymore. Every single individual spot will be a discrete drive. And so now you have to make sure that that's very, very uniform. The other problem is that a laser has speckles. And so, right, if you ever looked at a laser, you'll see it has sort of little dots. And these are now sources for perturbation. And so the little pits that we have on the capsule that we worry about, you now have that fundamentally in the laser itself. And so that's a problem. So now you need to introduce some smoothing to the pulse shape, which you can do. That technology didn't really exist 30 years ago, but we know how to do it now, we think. But as of yet, that's not been proven at scale. But so potentially, yes, this is the more efficient approach if you want to go for efficiency. Yes. No, not at all.
Okay, so we have to wind it up, but thank you so much for fantastic.
Thank you very much for having me. I appreciate it.